Welcome back as we continue our exploration of various inverse functions and their derivatives. And today, in the last section we're going to cover in AB calculus is going to be inverse trig functions. Here we go. I've written a function theta is equal to the inverse tangent of t, and I've written it like that to make you understand that when you take the inverse tangent, you're going to get an angle. You're getting an angle back. In fact, for the inverse tangent, you're going to get an angle between pi over 2. The range of this thing has to be between pi over 2 and minus pi over 2. Okay? The domain could be all real numbers. But let's draw a picture over here of this angle. That's going to help us we're going to call that theta. And actually, okay. So we're getting an angle theta. So anyway, what are we interested in finding? Well, we're interested in finding d theta dt. We want to know what's the derivative of this function. Okay. Well, once again, we do not know the derivative of the inverse tangent, but we do know the derivative of the tangent. We know if you would say y is equal to the tangent of x, right? dy dx is equal to what? This is the one we should know by now. That's the secant squared of x. So we know the derivative of the forward function. We're trying to find the derivative of the inverse function. What do? Well, we're going to apply a transform on this. We're going to say, well, I'm going to take the tangent of both sides. The tangent of theta is equal to the tangent of the inverse tangent, or the arctangent of t. What does that then become? That becomes just the tangent of theta, number one, is equal to t. Okay, let's go to work now. I think we can, now we're going to use, this is implicit differentiation problem, isn't it? We'll take the derivative with respect to time of both sides. And we're going to get what? Well, the derivative of the outside function, the derivative of the inside function is just d theta dt times the secant squared of theta is equal to, what's the derivative of t with respect to t? Oh, that's just 1. This would leave us with d theta dt is equal to 1 over the secant squared of theta. Now this is true. We would like, though, we get d theta dt as a function now of theta. I really want it to be a function of t. A function of t. So what is theta? Well, theta is the inverse tangent of t. I could write that, I guess, as this, the secant squared of the inverse tangent of t. That's not going to match any of my work, though. So I want to get the answer I'm looking for. What I do, I'm going to simplify this even more. I'm going to go up to this triangle. Okay? Now notice the tangent of theta. This says what? What this means here, it says the tangent of theta is equal to t. Tangent of, so what's the tangent of theta? The tangent is the opposite over the adjacent, right? So I'm going to make this side equal to t, this side equal to 1. So I'm using my triangle trigonometry. That's a right triangle. Okay? So t over 1, what's this side equal to? Well, this is just a little Pythagorean theorem. This is the square root of t squared plus 1. Okay, well, what is the let's go back to this definition here then. What is the secant of theta equal to? Well, it's equal to 1 over the cosine of theta. The cosine of theta is equal to what? The cosine of theta is equal to 1. It's going to be over adjacent over hypotenuse, right? So I go back up to my triangle. It's 1 over this, so it's 1 over square root of t squared plus 1. Cosine's equal to that. The cosine squared of theta is going to be equal to 1 over t squared plus 1. Well, notice that is equal to the cosine squared of theta, or it's equal to 1 over t squared plus 1. Okay, so what is the derivative? This get kind of messy here. Whoops. I'm going to do that. Go backwards here. The derivative of the inverse tangent is this. I better get my pencil right here. Okay, let's summarize. Let's put these things in there. I did a little derivation for you. You're not going to derive this all the time, but I did want to show you how, in general, if you know the forward function, I know the derivative of the forward function, I can then derive what the derivative of the inverse function. I've done that twice now, both for the natural log and now for the inverse tangent. I'm not going to do that every time. We do have to memorize some things. You know, I'm a big fan of memorizing as little as possible. So these are I'm not even giving you all the inverse functions, but I'm giving you 3 of them, right? Remember, for trig, I wanted you to know sine, cosine, and tangent. You can derive all the reciprocal functions. The same thing here. I want you to know the derivatives of the inverse sine, cosine, and tangent. We just derived this one here, right? We just derived this. The derivative of the inverse tangent is 1 over x squared, which means what? Well, there's a complementary antiderivative thing. The integral of 1 plus x squared is going to be equal to this. Okay. The inverse sine, the derivative of that is 1 over the square root of 1 minus x squared. Again, I don't have to read that, but just look at this. And then the antiderivative is that. Antiderivative of that is the inverse sine. Inverse cosine, the derivative is the negative of the derivative of the inverse sine, which to me says the inverse cosine is equal to negative the inverse sine. These are, which is kind of interesting. Okay. Anyway, so know these inverse trig functions. Again, in this chapter, we've introduced the exponential function, its inverse, the log function, and now we've introduced these inverse trig functions. What are we going to do next? Oh, we're going to review some calculus operations with a different function now, the inverse trig function. So let's look at a problem. Here we go. Here's an integration problem, and if we looked at this, and I'm going to try to look at it from your eyes, is that this is not one of the antiderivatives I know. I don't necessarily see, I don't see a substitution, although I do in part of it. I don't see, like, if the top was just x, I would say, oh, we got a substitution. But I see that 1 plus x squared pattern, and I want to keep that in mind. You see the 1 plus x squared pattern in the denominator. I'm thinking maybe if I can set this up, I can get an inverse tangent. And so the first thing I do is, since I see that, I see kind of a simplification. I'm going to break this up into 2 integrals, 1 over 1 plus x squared dx plus x over 1 plus x squared. See how I did that? I took, again, I broke this out. That's one integral. And then I broke this out as another integral. Now I'm going to work on this one. Well, this one fits my pattern perfectly, right? If I know that that is an inverse tangent. That's an inverse tangent. I'll put my plus C on this whole thing over here. Plus, so what about this, though? Here I see a substitution. Here I see a substitution. We'll do that in blue. I'm going to say U is equal to 1 plus x squared. Du is equal to 2x dx. Du over 2 is equal to what? X dx. Okay, so I saw the derivative here. I saw x dx is that. So then this becomes what? Du over 2 over u. Which will bring that down a little more. That's going to be 1/2 the integral du over u. You recognize that one? Again, I guess we haven't done too many of these yet, so let me just, if you would rewrite that, I'm going to take this over here and change to red, do a little bit on the side. I'm going to say u to the minus 1 du, and you should think like this. Oh, that's a power rule, over 0, and you see that, oh, and that should remind you, oh, wait a minute, that's the natural log. That's the natural log. That's the natural log of u. 1/2 the natural log of u. But notice I got a function of x, a function of u. I've got to put in my constant of integration. I want to go back to x, so I'm going to put this back in here. So this, back to blue now, and my answer, this is just going to be 1/2 the natural log of 1 plus x squared. This is going to be the inverse tangent of x plus c. Okay, and that's going to be the answer to that question. Okay, right here. Nice little review. If you take the derivative of these things, it should work. The derivative of the inverse tangent, oh yeah, that's that. What is the derivative of the natural log? Well, it's 1 over 1 plus x squared times 2x cancels that. Oh yeah, so that's going to match up with this. Okay, and of course my constant of integration. Okay, so again, we could do a bunch of these things, and you can practice some of these with homework. I probably have enough time for one more. Okay, I've got another integral here, and again, I got to get a couple more things in my head, memorized in my head, unfortunately, that I have this. I have this square root of 1 minus x squared dx. This is going to be the inverse sine of x plus c. So this kind of looks like that, but now I have a 4t involved here. So I want to massage this and make it look like that. I'm going to dt here, do a little work. 1 minus, look, if I put in 2t squared, that's identical, right? And now I'm going to do just a little substitution. I'm going to do a little substitution to try to make this look like that. I'm going to let x is equal to 2t. dx is equal to 2 dt. Or dx over 2 is equal to dt. Now I'm going to substitute in here. What do I get? Well, dt is just equal to dx over 2 over 1 minus, what's 2t equal to? X squared. Now that looks like 1/2 dx over the square root of 1 minus x squared. Well, those look remarkably the same, right? So that's just going to be 1/2 the inverse sine of x plus c. Okay, so a lot of these problems, what it comes down to is the form of these, right? I knew I had something that looked like this, and I did some substitution to make my integral into one that I know. Okay, still, let's remember, we'll probably put those up in a different slide here. What are the pairs of derivatives you need to know. In fact, maybe I'm going to stop it right now and write them all down. Okay. Okay, I thought I'd make a little list of what these derivatives and integral pairs that you should know. Just to remind you, it's not a very big list. It's not a very big list at all. And just to keep these straight, so each one of these, this is the ones you've known before. And if I put these in, what do we got? We got a power rule. We got a constant rule, which is really a form of the power rule. We've got some trig functions, forward trig functions, the sine, cosine, the tangent. I don't think it's necessary to memorize the derivative of the reciprocals. You could derive those. And we got the derivative of the exponential function. We got a derivative of the natural log function. We could derive the derivative of 2 to the x or log base 2 to the x. Those are not nearly as important, though, as the natural log and the exponential function, the e function. And what else besides? Those are 7. Then we go back to these inverse trigs that I had up here before. Here they are. How many did I forgot the number I was on. 7. Okay, so we're going to start with 8. 8, we got the inverse sine. Again, these are second order, but you should know these. These can show up. 8, 9, 10. 10 pairs. Not too many, and that's the complete AB list. Those are the ones you need to know. When you do an integration problem or a derivative problem, it'll be either use substitution to put it into one of these forms, or see the derivative or integral directly. Okay, well, that's chapter 7. Now we're on to differential equations, one of my favorite topics. See you soon. Bye-bye.